Welcome to qnawire.
So this is a bit harder in the sense that we need to model each molecule as a cube and then find the side length of that cube within this system. So if we were to say, okay, this system is a perfect cube, let's just draw this perfect cube. And then we're saying, okay, let's split this into, let's okay. So now let's split this and say, okay, this is going to be how each of our molecules are being modeled. Where at the center of each of these little cubes, there's a molecule. Okay? At that point, we can say, okay, what's the side length of one of these molecules? Now, this diagram may help you give you insight in what we're trying to do. So we're just trying to find the side length of this cube, and in the center of this cube, there is a molecule. So let's write down our givens. T equals 27 degrees Celsius. And in order to find Kelvin, you simply have to add 273 to the temperature in Celsius. So 273 plus 27 would be 300 Kelvin. And then our pressure is going to be 1 atmosphere. We can convert to pascals, so 101,325 pascals. And then we actually can say that N equals Na, where N is the number of molecules, so total number of molecules, and N is, of course, the number of moles. So let's first try to manipulate the ideal gas law and say that V would be equal to nRT over P. We're going to say that this is going to be the volume occupied by this entire gas. And we can define V prime as V over N, and this is going to be equal to the volume occupied by a single molecule. We're dividing the total volume occupied by the gas by N, N being the total number of molecules here. So we'll have V prime equaling the volume occupied by a single molecule. And then at this point, we can plug this equation into this equation. So we'll have V prime equals nRT over the pressure times the number of moles times Avogadro's number. Again, this would be P capital N, and then we simply just substituted this into this value, into this equation, and substituted this formula right here into this formula right here as well. So it'll be nRT over P times 1 over capital N, or nRT divided by P lowercase n up times Avogadro's number. Let's solve, and our moles cancel out. So now we can have 8.314 300 Kelvin. Our pressure is going to be 101,325. That'll be our pressure in pascals. And then the Avogadro's number, 6.023 times 10 to the 23rd. At this point, we say that V prime is going to be 4.08 times 10 to the negative 26 meters cubed. So if you were to think about this, this is the volume of a single cube. So this is a volume of a single cube, where in that single cube there is a single molecule. So we can say that V prime is going to be equal to the length, the side length, essentially, of a cube cubed, L cubed, will be L equals V prime to the 1/3 power, 4.08 times 10 to the negative 26 to the 1/3 power. This is going to equal 3.44 times 10 to the negative 9th meters. So this will be our side length. So this is our actual answer for A. If each molecule was modeled by a cube, with the molecule being the center of that cube, the side length of one of those cubes would be 3.44 times 10 to the negative 9th meters. 10 to the negative 9th denotes nano, so this would be 3.44 nanometers. And B is asking us, how does this compare to the order of 10 to the negative 10th meters diameter of a molecule? So it would be 30 times larger. So the side length would be 30 times larger than the diameter of a molecule. So side length 30 times larger. And then C says that the spacing with a solid is 0.3 nanometers. So this would be 3 times 10 to the negative 10th meters. And this is approximately 10 times. So at this point, so this is 10 times. So here it's actually going to be, the spacing is pretty close. It's only one order of magnitude off. So the side length is 10 times larger than spacing in a solid. So if this was a lattice parameter, 0.3 nanometers, we can compare this value to here. We see that there's one order of magnitude, so that would be the side length is simply 10 times larger than the spacing in a solid. So as you can see, if you find the ratio, 10 times larger is significant, and that's what makes this a gas. So spacing between molecules is much higher than spacing between molecules when they're solid, and that is what defines a gas. So for B, again, 30 times larger. For C, 10 times larger. And our final answer for that side length would be 3.44 times 10 to the negative 9th meters. And that's the end of the solution. Thank you for watching.